Okay, so lecture 2 for week 2 is going to be chapter 2 of mechanical behaviors, testing, and manufacturing properties of materials. So really we're going to focus on really tensile testing in a way, but we'll be talking about other impact tests and other things, which we're doing this week and next week in lab, right? So sorry this is getting a little bit later than I like to get videos out. I'm trying to still feel out the best way to do these videos, and I'm thinking for the 2 different lectures, rather than giving you 2 on Monday, I think I might split them up, do 1 on Monday, 1 on Friday, as like our 2 labs or 2 lectures that we typically have during the semester. So I'll probably try to get I really try to get them up by Thursday for the second, and then I'll give you until the next Friday. So you basically have it Friday morning. Unfortunately, this week, technical issues and dealing with books and everything else, I'm sure you guys are all aware of issues that everyone's having. So this chapter 2, again, material testing and material behavior, properties, so on. So topics really examine the effects of external forces on the behaviors of materials and the test methods employed in determining their mechanical properties. So we'll be going over really essentially all the tests that are typically done and what they convey to an engineer for design purposes, what properties you can understand from the materials. So we'll discuss tension tests, compression tests, how and why bending tests are used, material hardness and how they range in hardness tests, how fatigue is tested. I should fix that. And analyzed for material failure testing. Understand the types of and factors of involved in failure and fracture of materials. So failure testing, understanding types and the factors involved. Alright, so the one we'll be doing actually, our very next lab, we're going to be doing actually cold rolling, so unfortunately a lot of the stuff we talk about in the beginning of the semester gets spread out into labs throughout the semester. So this one will actually be not next lab, but the lab after. So our third lab will be doing our tensile tests. But what is that? What is a tensile test? And we saw the machine, so if you've been to the first lab, seen the machine, but basically you have this dog bone, which we've been calling it, piece of material, metal in most cases for us on MVCC campus, but this here gets pulled apart and you eventually get a fracture, right? So this is what's termed as destructive testing, and this is what you're seeing here is the variations in the uniformity of the elongation of the part before it eventually snaps, right? So it's showing L0, and you'll get used to these notations, especially if you do a lot of engineering work or go further in the math side of engineering. We'll be doing quite a bit for our courses, but if you go to 4-year degree, you definitely use these. But these are called subscripts. So here it's saying length 0 is initial, so our initial length. Our LE here is uniform elongation, so up to a certain point in our stretching here, we'll have uniform elongation. And what that means in most metals is, as we talked about our yield strength, and I that was one of the questions asked in one of the quizzes was, what is that when the atoms bonds start breaking and sliding from atom to atom, right? Well, this is called uniform elongation before that point. So before our yield points, this is a yield point here, and this is what's depicted on what's called a stress-strain curve. So before I go too much further, let me explain this curve. So this curve is generated through this testing, and what this shows is the elongation amount, so basically change in length here, strain, is then correlated to how much stress we're adding. So how much stress is going to depict how much strain we're going to have, how much stretching. And what the uniform elongation means it's in elastic deformation, meaning it's like an elastomer. It can go snap back to its original shape, right? As far as that's concerned, that uniform elongation, happens until this point. And then you end up getting a plastic stretching. So elastic, you get an elastic stretch here. And I think I mixed those up. So this would be uniform elongation to here. See if you don't have any necking. This is our elastic elongation. So elastic elongation, our elasticity point is right at our yield point. The uniform elongation goes all the way up until right to the tip, and this is actually why we see this bend and then a fracture eventually. Is we end up getting a necking, our area will decrease, and essentially that changes the amount of stress that part can hold, and it changes the equation they use to plot this. And later in the video, you'll watch a video called True Stress, True Strain, and they account for this necking. Right now this doesn't account for necking, but you're still able to see when the necking happens just because of what the curve does. So in this case, uniform elongation up until they're terming this UTS, ultimate tensile strength. So we're doing a tensile test to figure out what its ultimate tensile strength is, its yield points are, and when it's going to start deforming, plastically deforming, yield point, right? So really these are the two biggest important parts of this graph, as well as what we'll talk about later is modulus of elasticity, which is the slope of this line. So this just depicts where along the graph and what your dog bone here is doing. It's rather useful and straightforward if you get the right view for it. And I think this video, I'll see if this plays here. This should be just a video of a tensile test, right? So you can kind of see and correlate to what I'm talking about here.
This video is going to be a bit different to my usual videos.
I'm going to cut that out. This video I'm going to post after this video, one of the videos after this video, just to see what the true stress, true strain curve is. I was going to play it, but it's a longer video than I expected. So it's about 6 minutes long. Alright, stress versus strain plot. So, kind of should probably put this initially first, but this is something we're going to be studying here this semester. And this is, again, what we've been talking about, what we're able to get as far as material properties to use in equations and calculations and things that we do in engineering. They're pulled from a plot like this. So metals, plastics, they'll have a stress-strain plot. And what we're looking for here, as I mentioned before, is our yield stress. When does it start yielding? And a lot of times that's called the yield point, because once we get up to that point, it starts yielding, right? Ultimate tensile strength, again, our max amount of stress we can hold with that initial area. Once that area starts decreasing, so that necking, this is why we end up getting a reduction of stress here. And again, they'll be reviewed in the true stress, true strain curve. This is, I believe, just a definition, more information. So if you would like to go to this, I'm going to make sure to post these PowerPoints so you can go to the links and use the links that I have in here. Alright, so we're talking about yield point, right? So our yield point is that point where we start getting permanent deformation. And what this plot here is showing, so as that dog bone stretching, right, we hit our yield point. We start plastically plastically deforming, but then all of a sudden the load is dropped, right? So we aren't loading it anymore. Well, this is what happens. So you've already stretched it, so you can't necessarily gain this strain back. You're not going to get that length back, right? You'll get some proportional length that's proportional to your elasticity here. So again, you have a certain amount of elasticity, right? That's going to stretch back. And it looks like my video cut out. Camera. So unfortunately, I'll just take that out. So that snaps back. So you end up getting this snap back, but it only snaps back the same amount it would have if it initially yielded, right before it initially yielded. So you end up losing, or in another way, you end up stretching the part a certain length, and then what it'll do is, this is called elastic recovery. So this will come here. Then if you were to load it again, it would start at this point. So it's already strained, and it's going to start at this point, and then it'll continue on. And if you plastically deform it more, and don't break it, it'll come down to a different point, and so on, until eventually it breaks, right? So that's permanent deformation. So it's actually yielding or stretching that part. See if I can get my video working. Nope, still frozen. Alright, I don't know what's going on with that. I'm gonna move on. Don't want to make this video longer than necessary. True stress, true strain curve. Essentially, what's I'm not gonna go into this very deep right now at this point, just because again I have another video I'd like you to watch. But we have true stress and true strain. Really, the difference is the correction for that necking. So as I mentioned, that necking in the part. Here we go, fracture and the neck there. So this is the necking they're talking about. So we have a neck, and that's when that changes. So we looked at stress strain curve. This stress strain curve's calculated with P over our force P over area, initial area, cross sectional area. When this starts changing, we don't necessarily take that into account. So that video will cover that. So I'm again not going to get very deep into that right now. And again, he talks a little bit more about the math, but basically you can calculate true stress, true strain curves given the correct material properties. And here's just a sample of a bunch of true stress, true strain curves. So you saw initially the first one had this drop off and then it breaks. True stress, true strain. The strain will keep going up, actually, or the stress rather will keep going up. The area next down, so you don't necessarily lose stress in that case. Really, you keep going up. So that's why they call this true stress, true strain. All right. So again, I didn't want to spend too much time on that since there's a brief video after this. All right, stress variations due to temperature. So in this plot here, we can see properties due to temperature, something that's rather important, especially thinking about how much temperature changes in all parts of the world, especially anybody that lives in New York realizes how big of a fluctuation in temperature you can get, and things tend to get brittle in the wintertime, right? So you end up seeing quite a bit difference of, say, temperature range. In this case, we have temperatures ranging from 0 degrees Fahrenheit all the way up to 1400 degrees Fahrenheit. And I think this is just, carbon steel. Okay, so this is carbon steel. So as we get, and you can think of things getting more brittle, less, it's not going to stretch as much. You end up seeing this drop, right? So we got this drop down to here, and you see we get less elongation. So elasticity, modulus elasticity, is essentially gonna stretch less. So we're gonna end up getting less of a stretch for that. So it's gonna take basically trying to think of how they would plot this. Thinking of it as like yield strength, and maybe that's a better one to look at. So that yield point, again, where that elastic modulus ends, what we see is our yield strength will actually tend to go up, but our elongation goes down. So what we end up getting is less stretching, right? So we might get a little bit higher yield point, but then things are going to basically break very quickly. And again, you see this tensile strength actually goes up as you can think of it in another way, is if you get hotter, right, things get easier to stretch, right? So in this case, you end up getting a higher yield point, but again, it ends up stretching less. So you end up getting a shatter or a crack rather quickly. That gives you an idea of how to think about stress variations due to temperature. Next one. There we go. All right. One other testing method that's used in, well, a little bit, not as readily as tensile testing, but it is used in various different fields, especially if there's going to be any compression for parts. They're going to want to see when, under compression things start changing. But you can get a similar curve from compressive loading. So instead of tensile loading, you compress it, right? The difference here and why this isn't used as much is because of this barreling effect. So what they show here is a barreling. And what that means and why that happens is there's friction. So there's friction on both of these plates. So as this gets crushed, rather than this being able to slide out smoothly, right, it gets stuck. It's going to get stuck on the plate because there's even a minute amount of friction is going to end up getting screwing up test results. So you get this barreling effect because this bottom material and the top material that are connected to the plate are actually kind of sticking to the plate and moving out not quite as quick as, say, the center that doesn't have that restriction due to friction. So you end up getting, a similar stress strain curve, but it's, again, not as precise due to that barreling effect. Other different types of destructive tests that are used quite a bit, especially in civil. You start thinking about loading for civil engineering. Buckling actually is a big test for rockets as well. As you might imagine, there's a lot of compressive force on a long cylindrical rocket. You can get compressive loading. And there's a video that I typically show my students, a NASA video that talks about the different testing they do for new technologies that are coming out. And in the sake of time in my recording here, I'm going to skip the YouTube video. Something I'll let you to go to later. Excuse me. It's just a quick video on what a buckling test looks like. Disc testing. So disc tests on brittle materials show the direction of a loading and the fracture path. So disc tests, again, for brittle materials, think ceramics, maybe glass, rather brittle, and you want to see the fracture path. So basically when under what load, when does that fracture and how does it fracture? So that's a fracture test, and I've heard of these being done quite a bit with, again, brittle materials, so ceramics, and in glasses they end up doing a test like that. So ceramic engineers tend to do a lot more of those types of tests. One other type of test, we unfortunately don't really conduct this one in lab, just because our torsion tester is seen its number of days. I might try to revive it and recalibrate it. But what you're trying to do for a torsion test is really anything that comes under torsion. So if you're using motors, drive systems, you're going to want to make sure that, say, your drive shaft or whatever you're running here, that under torsion isn't going to shear, right? So there's torsional shear as well. When we talk about tensile stress, but there's also shear. So the shear happens here, can be recorded with a test that essentially spins this dowel here. So you notice the arrows here. So we spin this dowel, and the number of times this spins, the number of degrees it's able to spin, gives us some information on how much loading it can take, under what load does it start stretching or plastically deforming, and then under what stress does it actually snap or shear. And again, there's another video here of a shear test, and I might go to try to click and clip these in my video when I go to edit, but most likely I'll probably just let you guys watch these yourselves. Bending test. So a bending test is exactly what it sounds like. Another test for brittle materials, really highly used in ceramic engineering. Again, my brother was actually a ceramic engineer, and he actually did these tests. So again, it's brittle materials. You typically don't do this with steels, depending on what you're trying to test for. If you had certain loading, you might want to do a test like this in this fashion, but usually, again, it's for brittle materials. You can actually predict bending in steels and things using strengths of materials and different calculations. So hardness test. So this is something we did this week. So most of you guys, or at least half of you all, have kind of conducted this test already. Rockwell hardness tester we use in lab. So ours doesn't look quite like this one. This one's digital. Got a control panel. Those are pretty expensive. So we have the dial ones at MVCC. So if you haven't used those this past week, you'll be using them this next week. As far as how those tests are done, so what is a hardness test? I didn't really explain. This is a puncture resistance test. So how much resistance does it have to puncturing a device? Or how deep can you puncture a device? And these are the tips. These are the tips that actually puncture the metal or whatever you're testing there. Typically metals in this case. We, again, use Rockwell. And if you notice, they have a lot of different scales for Rockwell. The ones we'll use in lab are the C and the B. The C is a diamond cone tip, and this is meant for high strength materials. So high puncture resistant materials like titanium. B, unfortunately, I don't think we have titanium to test. That might be something we'll look for when we do our heat treat. Maybe not, we won't be using titanium to do a heat treat, but we'll use a harder metal that we can use a C tip for. Our lab will be using our B tip, so Rockwell hardness B scale, and this is a 1/16 inch ball diameter. So it looks like this, and you end up basically trying to push this ball into the metal, and depending on how far it goes, it's really minute amount, but it's enough to actually get a reading off, and then using this, it can take how far it's actually gone into the material and multiply that by 500, subtract it from 130, and you get your HRB reading from that, or subsequent readings. But like I said, we'll be doing HRB and HRC. The Bernil hardness test. This is something, again, we have in lab, and maybe I'll show a demonstration at least with this. These are a little bit harder to do because you also have to have magnifying glass or a scope to look down. So this essentially, you do the same test and you push a ball into a piece of metal using a high amount of force. D here that we're actually looking at, so we have two diameters. Really, we're looking at basically the divot kind of that it leaves, the edge to edge measuring distance. And this is what Bernil hardness tests do. They look for that measuring distance, and then they apply it to this here. So D would be your impression. Large D here would be the diameter of your ball. It's weird that it would show lower D over here. But basically, yeah, you're doing this calculation, and the loading you're putting under it, and it'll give you your hardness reading. So it's essentially the same as a Rockwell hardness test, except for this one measures depth, this one measures diameter, or diameter of impression. And for most scales, it can be a little tedious from time to time to try to correlate what one hardness scale correlates to on another scale. This is one I've gotten out of the book material, and you can see we can take an HRB reading and correlate it to a Rockwell Hardness Scale C reading, or correlate our Rockwell Hardness B reading to, say, our Bernil tester, or any other different types of scales we want to. It can be a little odd. Again, you can kind of see how it shifts weird. Like the Rockwell Hardness A scale goes from 40 to 85. HRB goes from 0 to 120. It jumps around a little bit, but they do correlate. Obviously, if you were in the 10 on the HB, which I believe is your Bernil hardness, I don't know why they switched the acronyms around, but if you were at a 20 here, you wouldn't really be able to correlate that with an HRC or an HRB. So, depending on your material, you might need to use a different test. And this gives you an idea. So lead, rather soft, right? And all the way up to a diamond, rather, the hardest substance. I know of, anyways. Maybe wrong on that. Endurance fatigue testing. So fatigue testing is meant to test for essentially that, fatigue. So flexing back and forth and back and forth. Eventually, you're going to break. And we don't have this in lab, but what this shows is an example of this test. So they put, I think, 100 kilogram weight on here, and it holds a specific amount of weight. And this device here flexes back and forth, and it'll count the numbers of times it's able to flex before that actually breaks. And that's known as fatigue testing, because you're fatiguing it back and forth, right, until it fractures. There's another type of destructive testing. Unfortunately, we don't have one of these, but you could easily test the fatigue of a paper clip. Well, more or less. It's hard to bend one in the same spot over and over again, and that's because of work hardening. Alright, material endurance limitations. So obviously all materials have specific limitations. So this one is showing endurance limitations, number of cycles until it breaks, stress amplitude, what's the max stress, what's the max number of cycles, and this is 10 to the number of power of 6. So would this be, I believe, 1,000,000? So it'll be able to flex 1,000,000 times for aluminum alloy at a certain stress. So you can actually calculate when you're going to end up having a fatigue or a failure. And this is something that's done for life of product typically. And usually endurance tests for a lot of machinery go through long tests until essentially it breaks. So it might even be hooked up, if an electrical device hooked up to a wall, you might run it a month or more and watch until it breaks. They want to know how long it's going to last, how many hours you can run it. Just a simple chart for a simple enough chart for showing a comparison for endurance limitations. So again, you got your tensile strength, how much tensile strength you're holding on that part, and your endurance limit here. And they just have two. So this is metric up here, and this is English. They're both tensile strength. This one here is just the endurance limitation tensile strength over tensile strength. So they have a relation here between endurance limit and that tensile strength. So you get an idea of, say, your endurance limit of these specific metals, just correlating them. As you might expect, titanium has quite a bit more of an endurance strength than, say, aluminum. Alright, material creep. What is it? So this is kind of something I don't really get into in depth necessarily, but essentially what creep is you can think of it, I always use a bolt as an example. So you tighten down a bolt, and that bolt holds the machine in place. Well, when you tighten it down and you really crank down on it, you're kind of stretching and stressing that metal, right? So you're putting a tension on that metal, that bolt. Well, that bolt, over a long period of time, you end up getting this, time and the amount of strain you end up having. So over a period of time, your strain is going to go up, meaning you're essentially stressing that metal, and eventually it kind of stretches and eventually ruptures. So this time and the amount of strain on a device, you initially under load, you put it under this instantaneous deformation, and then over time that strain kind of builds. So this is linear segment of curve. Secondary is used to design components for a specific creep life. So how long, again, is that bolt going to last for that purpose? This is a test we have in lab, but we haven't necessarily run it due to some issues, calibration issues, and different things. I'll have to check to see if it's working this year and whether we can run this lab. I'm thinking we're probably not, since we're on a pretty strict schedule for what we have and what we have time for. But the impact test, what this tells us how much of an impact or a hit something can take. So in this case, it'll hit, and we'll actually get to see, well, how far does this swing? So the neat thing about physics is you have a certain amount of energy, like potential energy right here. So it's held in a very specific starting position, and that head of this hammer here weighs a very specific amount. So it has a very specific amount of energy being held here. So when we release that pin, this hammer drops, hits the specimen, and you can actually see end of swing here is a lot less. If it didn't have a specimen in there, it should swing exactly equal to the other side, right? Well, in this case, it breaks that specimen, and it's only going to swing a certain amount. And between that height there, we can actually calculate how much energy is taken by the sample. And that's what impact testing is. And the typical two types that you run for impact testing are IZOD and Charpy tests. And really the difference between them is how you hold them in the device and how the hammer hits. So if you notice the opening of this notch here is facing toward the hammer, and it's sticking straight up out of the ground. And this one's held, kind of horizontal to the ground. And the hammer hits on the opposite side of that V cut. So again, your samples are very specific in size. The cut is very specific in its dimensions. So you can actually get very accurate information of that material and how much impact that can take. Alright, so we'll be stopping here on impact testing, and next week we'll pick back up with our failures. Material failures, that is. So I guess everybody have a great weekend, and I'll be talking at you next week. Alright, later.